Hi dear students, I am Kamala Soppin, Assistant Professor of Physics, DRM Science College, Davangere. Today we are in the session 2 of Elasticity chapter in BSc Physics first semester. In this session, we are going to discuss relation among the elastic constants. After the completion of this session, you will be able to know the relation among Young's modulus, bulk modulus and Poisson's ratio, the relation among Young's modulus, rigidity modulus and Poisson's ratio, the relation among Young's modulus, rigidity modulus and bulk modulus, and the relation among bulk modulus, rigidity modulus and Poisson's ratio. Then for this purpose, we have to consider one solid cube of unit side. Here A, B, C, D, E, F, G, H is a solid cube. It has unit side, unit area and unit volume. Here we consider the forces P and P which are acting along the x direction. Here if you observe here, this is P and P. They are acting along x direction and these forces produce expansion along x direction and contraction along y and z axis. Similarly, the forces Q and Q are acting along y axis, produce expansion along y axis and contraction along x and z axis. And the force R and R are acting along the z direction and produce expansion along z axis and contraction along y and x axis. Then here we discuss the longitudinal strain. It is the ratio of expansion to the original length, expansion or compression to the original length. Lateral strain is defined as change in the length in the lateral direction to the original length. The original length of the cube is unity. Hence, the expansion along x-axis is equal to longitudinal strain and it is taken as alpha. The contraction along y and z axis is called lateral strain and is taken as beta. And Young's modulus is equal to normal stress to the longitudinal strain and it is equal to, stress is given by force per unit area. Here force is P and area and the longitudinal strain is alpha, and we know that area of the cube is unity. Hence Q is equal to, Young's modulus Q is equal to P by alpha, or the longitudinal strain alpha is equal to P by Q, where P is the force along x-axis and Q is the Young's modulus. Then the Poisson's ratio sigma is given by the ratio of lateral strain to longitudinal strain. Therefore, sigma is equal to beta by alpha, or beta is equal to alpha into sigma, or beta is equal to sigma as it is and alpha is equal to P by Q. Thus, due to the force P, the elongation along x-axis is given by P by Q, that is alpha, and the lateral contraction along y and z axis are sigma P by Q and sigma P by Q. That is, these are the lateral strain. Similarly, due to the force Q, The elongation along y-axis is Q by Q, and the lateral contraction along x and z axis are sigma Q by Q and sigma Q by Q. Due to the force R, the elongation along z axis is R by Q and lateral contraction along x and y axis are sigma R by Q and sigma R by Q. Therefore, due to the force P, the expansion along x axis takes place and compression along the same x axis takes place due to the forces Q and R. Hence, the net elongation along x axis is equal to P by Q minus sigma Q by Q minus sigma R by Q. The net elongation along y axis is equal to Q by Q due to the force Q, and due to the forces P and R, the compression takes place, and hence we have the negative sign here. Q by Q minus sigma Q by Q minus sigma P by Q and minus sigma R by Q. Here. Then the net elongation along z axis is R by Q minus sigma P by Q minus sigma Q by Q. And here we assume that all the forces are equal. That is, P is equal to Q is equal to R. Then the net elongation along x-axis, and here in this equation we have to substitute P is equal to Q is equal to R. Therefore, P by Q, we have net elongation along x-axis is P by Q minus sigma P by Q, and it is equal to P by Q is common. We have remaining is 1 minus 2 sigma. Like that, the net elongation along y and z axis is equal to P by Q into 1 minus 2 sigma. And here the elongation is also elongation along x-axis is equal to P by Q into 1 minus 2 sigma. Then for y and z axis, that means for perpendicular directions, we have the elongation is a P by Q into 1 minus 2 sigma. Then the original volume of the cube is unity. The new volume of the cube, because there is elongation along x-axis takes place, there is elongation along y and z axis also takes place. Therefore, the new length is 1 plus P by Q into 1 minus 2 sigma along all the directions x, y and z directions. Therefore, the new length is cube, Q raised to the new volume of the cube. Therefore, the new volume is given by 1 plus P by Q into 1 minus 2 sigma whole cube, and it is approximated as 1 plus 3P by Q into 1 minus 2 sigma using the polynomial function 1 plus x to the power of n. The polynomial function 1 plus x to the power of n is expanded as 1 plus nx plus n into n minus 1 x square divided by 2 factorial etc. Here the higher powers of x, which is 1 minus 2 sigma, are neglected. Then the increase in the volume of the cube is equal to the new volume minus the original volume. New volume is 1 plus 3P by Q into 1 minus 2 sigma. The original volume is 1, then plus 1 minus 1 get cancelled. We have 3P by Q into 1 minus 2 sigma. Then the bulk modulus is equal to normal stress by volume strain, and it is equal to P by area. Stress is P by area. Then volume strain is change in volume to the original volume. Then K is equal to P by 3P by Q into 1 minus 2 sigma, or K is equal to Q by 3 into 1 minus 2 sigma. This is equation 1. This is a relation among the bulk modulus, Young's modulus and Poisson's ratio. Then let P is equal to minus Q. We assume that P is equal to minus Q and R is equal to 0. Let P is equal to minus Q and R is equal to 0. The net elongation along x-axis is equal to P by Q plus sigma P by Q. That can be obtained by this equation here. From this equation, here we have to substitute P is equal to minus Q and R is equal to 0. If R is equal to 0, there is no third term here. And if P is equal to minus Q, therefore minus Q is taken as P. Therefore P by Q is common. We have 1 plus sigma, like that. Here, the net elongation along x-axis is equal to P by Q here plus sigma P by Q. P by Q is common. We have 1 plus sigma remaining. The net compression along y-axis is equal to P by Q plus sigma P by Q, and it is equal to P by Q into 1 plus sigma. And here we have elongation along x-axis and compression along y-axis, and x and y-axis are perpendicular to each other, and we have the same value of elongation and the compressions in the perpendicular direction. Therefore, the shearing strain theta is equal to the sum of elongation strain and an equal compression strain in a perpendicular direction. Therefore, the shearing strain theta is equal to P by Q into 1 plus sigma plus P by Q into 1 plus sigma, the summation of the elongation and compression in the perpendicular directions, and it is equal to 2P by Q into 1 plus sigma. Therefore, the rigidity modulus is given by tangential stress to shearing strain. Tangential stress is equal to P by area and shearing strain is equal to theta. Then substituting those values, then N is equal to, here we have N is equal to this expression P by 2P by Q into 1 plus sigma, and P get cancelled, Q goes to numerator. We have N is equal to Q by 2 into 1 plus sigma. This is the relation among the rigidity modulus, Young's modulus and Poisson's ratio. Then from equation we have Q is equal to 3K into 1 minus 2 sigma, and 1 minus 2 sigma is equal to Q by 3K, and our 2 sigma is equal to 1 minus Q by 3K. Then from this equation 2, we have 2 into 1 plus sigma is equal to Q by N here. Then 2 plus 2 sigma is equal to Q by N, or 2 sigma is equal to Q by N minus 2. And hence this is also 2 sigma and this is also 2 sigma. And equating these two equations, we have 1 minus Q by 3K is equal to Q by N minus 2. And simplifying this, we have Q is equal to 9Nk by 3K plus N. This is equation 3, and this is actually the required equation. This is the relation among the three elastic constants, Young's modulus, rigidity modulus and the bulk modulus. This is actually the required equation. Then from equation 1 we have Q is equal to 3K into 1 minus 2 sigma. From equation 2 we have Q is equal to 2N into 1 plus sigma, and equating these two we have this one. Then sigma is equal to 3K minus 2N by 6K plus 2N. This is a relation among the bulk modulus, rigidity modulus and Poisson's ratio. Okay, the equations 1, 2, 3, 4 give the different relations among different elastic constants with Poisson's ratio. Then questions of this session are: derive the relation among K, Q and sigma. Derive the relation among N, Q and sigma. And derive the relation among K, N and Q. Derive the relation among K, N and sigma. And some of the reference books are as follows. Thank you.